So today we are going to take a look at very simple recursion, examples of recursion in Haskell, and the first program is going to be something that does a factorial. That's what we're going to call it, and I think all of us know what a factorial is. Uh, Factorial 1 will be pattern match 1 is 0, and fact n is n times factorial n minus 1. Okay, so that is what factorial is. Let's well, let's just put in let's just typecast this. So fact typecasted is something that takes an int and returns an int. So that's your factorial function. Let us quickly write a main function. So we will put a string saying input a number, and we will read that into a variable called a line, and then we'll say b is factorial a, and we will put string factorial. We will print b. So there you go. That should work in principle. So we do compiling of the code. So we'll use GHC, give the file name .c, sorry, hs, no, hs, and we should be able to run it. Recursion, and if we put a number like 5, oh, mistake, the factorial of 0 is 1. That is a big mistake. Okay, so let's do that again. Okay, let's put a number like 4, and the factorial is 24. Pretty simple stuff. Okay. There. This is not very efficient, but we'll take a look at how we can make it more efficient a little later. By the way, you can probably also go to JCI, okay, and let's say you want a factorial of 5, okay, then you can say 1, 2, 2, 5. That'll give you an array that goes from 1 to 5, and if you multiply, okay, fold left, and you give it the multiply function, and you give it an initial value, just so you know, that would also be a way of calculating a factorial, and this would probably, very probably, be a much more efficient way of doing it. Okay, but you can do it using recursion as well. The next function that we're going to look at is going to be the Fibonacci number. Fib, we'll call it fib, and we're going to take, just like previous, we are going to take an integer and we are going to print out an integer. Okay, and the Fibonacci number for a 0 would be a 1. Fibonacci number for a 1 would be a 1 as well, and Fibonacci number of, say, n is going to be the Fibonacci number of n minus 1, okay, plus the Fibonacci number of n minus 2. Okay, you can put them in function. You can put them in brackets if you want to be extra sure that they're gonna work. Should be okay without the brackets. And you can go ahead and compile it. Yeah, it works best if I put the right values in. And of course, we should go ahead and see is Fibonacci of a, and let us also print it. Okay. Fibonacci is C, and we should be able to get the Fibonacci number for C. Okay, let's try to compile this, and looks like it worked this time. So let's see what it gives us. Recursion will put 4, and the Fibonacci number of 4 is 5. So 1, 1, 2, 3, and 5. Okay, so well, that's Fibonacci. We will do another problem called the Tower of Hanoi. Okay, and before we go ahead and do this, let me explain what it is. Okay, and then we'll come back and do this. Okay, so here's the Tower of Hanoi problem. Okay, it's a really simple problem. It has 3 pins, and we'll just call them P1, P2, and P3, and it has a number of disks. The real problem has 64 disks. We will simulate it using only 4 disks. This is just for illustrative purposes. Anyway, so the idea is that the disks, the 64 or 4 disks in our case, they're of different sizes. All of them are different sizes, and the disk that is the smallest will always be on top, and the nth disk from the bottom will be bigger than the n minus 1th disk. Okay, so this disk is going to be bigger than the one on top of it, and that in turn will be bigger than the one on top of it, and so on and so forth. Okay, so now the problem is to take a disk from move all the disks from one of the pins P1 for example into another disk P2, using a third disk P3. And the reason we need a third disk is because we can move only one disk at a time. So if the problem contained only one disk, you could just move the top disk from P1 and move it to P2. But if you, for example, had two disks, let's for the moment forget about uh, the third and fourth disks. Let's say we had only two disks and we wanted to move the top two disks from P1 to P2. This is how we would do it. Okay, we would take the top disk over there and we would move it to P3, and then we would take the top disk from um, P1, and then we would move it to P2, and then we would take the disk that we have in P3 and we would move it to P2. So this is what I mean by using the third pin to move a stack. Okay, so let's do one thing. Let's move them back into P1. And here's the problem. Let us say that we want to move 4 of the disks from P1 to P2 using quote unquote using P3. What we do is in recursion, okay, we say we move n minus 1 disks, in this case 3 disks, from P1 to P3, okay, using P2. Okay, so we will move from P1 to P3 using P2. We will move one disk, because we only have one disk over here, from P1 to P2. Okay, that should be simple enough. And then we will move 3 disks, n minus 1 really, but we'll just call that 3 disks. We'll move them from P3 to P2 using P1. So that's the algorithm. Okay, now let's figure out how to do it in Haskell. Okay, so now that we kind of know what the problem is, the Tower of Hanoi, we will go ahead and we are going to solve this problem using Haskell. So the Hanoi problem, okay, it's going to take a particular number of disks, so we'll call that that would be an integer, and we are going to call the pins by some name, so we'll put strings uh, okay, as the name of the pins. So that would be pin 1, that would be pin 2, and that would be pin 3, and the output would be a string. Okay, sorry, it would just say that you take something from this pin to this pin. So the output is going to be a string as well. Okay, now before I go ahead and solve this, okay, let's review factorial and Fibonacci to just look at what the general rules for doing recursion is. It's basically writing down what you want to do and specifying the boundary condition before your general equation. Okay, that's what happened in factorial, and that is also something that happens in the Fibonacci sequence. Okay, you write down your general equation, and before you do that, you go ahead and write down your terminating conditions. Okay, so now for the Tower of Hanoi, okay, let's write down the um, terminating condition later. Let us first write down the condition for the general solution. Okay, so Hanoi, let's say we have n disks and we want to take them from pin, sorry, we want to take them from pin 1 to pin 2, okay, using pin 3, just like we had done before. Okay, so what we're going to do is we are going to take, okay, um, n minus 1 pins, okay, from pin 1 and put it in pin 3, okay, using pin 2. Okay, that is the first step. The second step is that we are going to take one pin, okay, just the one pin that is left in P1 and move it to P2 using pin 3. Okay, and we don't really need to use pin 3, we put it there just because of the way in which the um, function is structured. Okay, this is kind of a dummy variable, you don't really need that, but in Haskell, being a strongly typed system, you have to put that in. Okay, and you then take all the stuff that was in pin 3. So you took n minus 1 pins and put them in pin 3. Now you take the n minus 1 pins from pin 3 and put them into pin 2 using pin 1. Okay, so that's exactly how we did the problem in the picture. Okay, that's exactly what we are doing over here, except that we haven't put in the terminating condition. This is the terminating condition. Okay, if we have one pin, P1, P2, and P3. Okay, if we have the terminating condition, then what you do is you just say from P1, okay, to P2. Okay, so when we just need to move one pin, okay, we just move the top pin from pin 1 to pin 2, okay, from here to here. And let us go ahead and say Hanoi A, and let's go ahead and print it. Put str and then let us put a line after this, Hanoi, and let us str, let's put D, because that's what we are getting. We're getting a string. Okay, so hopefully everything is okay, and let's compile this. Ooh, let's see what the problem is. Type string with actual type string. Okay, there seems to be a problem. Oh, okay. Well, we have to put in the names of the pins. Okay, so there you go. You have pin 1. I'm sorry about that. Let's just call them P1, P1, P2, and P3. Okay, and this should work, hopefully. And let us run recursion, and let's do 3. And the factorial of 3 is 6. The Fibonacci is that. And the solution for the Hanoi problem for getting 3 pins from P1 to P2, okay, is that you can kind of verify that. Okay, so there you go. That's very simple recursion.